All right, let's get started. So I don't have a presentation. We're just going to do some examples for Bodie plots. And it's just a process, right? So let's define the process. And A number one is start with a transfer function. And I actually started working on doing a high pass filter transfer function. R1. Oop. This is what I was going to show you how to do this morning, but then I scrapped it and I'll show you why in a second. Oh, geez, this is C2, R2, and this is a bandpass application, right? So I actually was going to show you how to do a bandpass filter, but the problem is to actually solve for the transfer function on this, it gets to be a lot of algebra to do it, and it took me 10 minutes to come up with a transfer function, which in class, I don't think you guys want to spend 10 minutes doing algebra trying to come up with a transfer function. But in any case, if you actually need to do a transfer function, you need to go back to what we've learned, right? In electric circuits, we have R's, L's, and C's, and then we have inputs that you can convert those to the Laplace domain. In mechanical systems, we saw some of the corollaries there, and we didn't do anything with chemical or civil systems, but there's a lot of basic concepts that you can apply. So somehow you got to start with a transfer function. Okay. And then our next step, and this is important, which is set up in standard, we'll call it configuration. And what I mean by that is, and I'll just give you an example here. You have to have S divided by whatever the break frequency of the polar zero is, added to 1. It always has to be S divided by the break frequency, added to 1. That's super duper important. And the reason why it's super duper important is because when we do magnitude of our gain, this has been a month and I'm still sick for what it's worth. So the magnitude of our gain, all right, has to have some sort of a general form of omega over omega 1 squared plus 1. And the reason why we do that is because we see that when omega is much, much less than omega 1, or whatever break frequency you're looking at, that omega over omega 1 squared term becomes a really small number. So 1 plus a really small number square rooted is still just 1. So if we don't set up this step right here, we don't have our Bodie plot approximations that are going to work out for us for our break frequency. So it's super important to divide by the break frequencies. Okay, that's setting it up in standard form. Now, there's one thing that I haven't included in there. I've divided out all the omega 1s, omega 2s, omega 3s, and omega 4s. They have to end up out front here, right? Because when you factor them out, they end up out front. So when you factor all of those out, you have this term over here. That is your scale factor. So your scale factor in this case is here. And all the scale factor does is it's a real number, and it's going to scale up or down your Bodie plot, your magnitude Bodie plot. Okay? So that's step 2. Now you're ready to start doing asymptotic Bodie plots for each individual pole, zero, or scale factor. So draw individual Bodie plots using, they call it asymptotic. And I should have added in here magnitude Bodie plots. Okay. And the key about this is it starts, so the asymptote starts at the break frequency. And it either goes up or down. And goes up. This is for pole 0. Or down. This is for a pole at 20 dB per decade. Or if you want to do a lot of refinement, another approximation is anybody know what an octave is? Well, I know I have some musicians in here. What is an octave?
Level of music. It's like your A chords, your E chords, C chords, E chords, E chords. And the different levels, those are all different frequencies. Those are
you said a very key word, different level of different frequencies. Are they different levels? Levels to me means power, like more power in, more power out. But a chord is a different frequency, right? The A chord is, I don't know what it is for guitar, but it's a very specific frequency. Same thing with C and all those different ones, right? So an octave is 2 times the frequency. It's a doubling of frequency. So when you say 1 octave above, you're double the frequency that you have. That's all that means. It's math. Music is math, isn't it? All these chords, when you hear a chord A, let's say it's something that oscillates at 360 hertz. If you want to go 1 octave above, it's 720 hertz. What's 1 octave above 720 hertz? It's 1080, right? No. It is a doubling of the frequency. So 1 octave above 720 is 1440. Okay, you double the frequency every time. You're not doubling that first number. So you go from 360 to 720 to 1440, not to 1080 or whatever. And then once you have that, draw individual phase Bodie plots using asymptotic approach. And this is a little bit different. So sometimes it's a little harder to do. I think it's a little harder to do the phase plots, but the asymptote starts at 0.1 times the break frequency. And ends at 10 times the break frequency. So this is quite different, right? Because when we talk about magnitude, it always goes up at 20 or down at 20. Each polar 0 always does that. For phase shift, it only goes up plus or minus 90 degrees. So it can't go on for forever. There is one thing that can go on for forever, but most cases, you're going to have it only go up or down for 90 degrees. So we have to start it at 0.1 and stop it at 10. Okay. And so right at the break frequency, what should the phase shift be? What's the phase shift? If you start at 0.1 and you go to 10 and you go 90 degrees, right? What would be at 1? 45 degrees, isn't it? 0.1 to 1 is 45 degrees. 1 to 10 is 45 degrees. So you're at 45 degrees at your break frequency. And then the idea is it goes up and down again at 45 degrees per pole or zero, exactly the same. And step 5 is add them together. Then you're done. All right. So let's do one. Let's do a nice, hopefully, simple example if this would ever stop messing around. All right, let's pick a moderate one. All right. So here's my transfer function. This is my closed loop, my open loop transfer function. That's going to be equal to, let's see, S plus 3 all over S plus 50 plus S plus 200. We want to draw the Bode plots for that. All right. Okay. So step 1 is set up in standard form, which means we have to divide out all the break frequencies. So in the numerator, we factor out a 3, which means this becomes S over 3 plus 1. In the denominator, we factor out, we have S plus 50 plus 1. That means we have 50 out here. And we have to factor out a 200 over here, which means we need a 200. So my scale factor is 3 divided by 50 times 200. Okay. So I should say this is step 2, right? I have my transfer function. Step 2 is to set up in standard form. We've just done that. Now we are ready, almost ready, I should say. We're almost ready to go ahead and do our plotting. Well, let's go ahead and do our plotting here. Let's call this step 3. So the first thing I need to do is find out what this is in dB. Why are we doing that in dB? Because we're using our Bode plot. And I'm going to plot that here. What type of paper is this? Semi-log paper, right? This axis is logarithmic, and this is just standard or regular. Okay. So now I'm plotting dB. So this is dB on this side, and this is frequency on this side. This is dB gain. And we want to convert everything to dB because it makes things so much easier. So for my scale factor, I have 20 log 10 of my scale factor. That's the only one that I need to calculate because each of these other ones are already doing 20 dB per decade or 6 dB per octave. So when I do 20 log 10 of my scale factor, I'm going to have to do that in MATLAB because there's no way I can do that on the top of my head. Excuse me. So I go 20 times log 10. In MATLAB, you got to use log 10 because if you just type log, it's natural log of 3 divided by 50 times 200. Oh, I forgot to close the parenthesis. Minus 70.4576. Minus 70 point, we'll just call it 5 dB. Okay. So now I'm going to go ahead and start to append onto my chart here. And let's say that this is minus 40, minus 60, minus 80. Actually, no, I don't want to do that. Let's start off with 20. You'll see why in a second. This is 20, 0, Why are the lines? Hold on, is it just plotting weird? Yeah, it's plotting weird, so I don't know why some lines are darker. 20, and you can also, if you don't want to jam it up so much, let's put this as 0. Let's put this as minus 20, minus 40, minus 60, minus 80, minus 100, and minus 120 dB. So now I'm ready to start plotting. And I can see that this is minus 70.5. So I'm going to use a red line to indicate that. That is my scale factor. Okay, that's my first one. Now I'm going to change my color. And I'll pick green. So now what I'm going to do is the dB for S over 3 plus 1. That's a 0. So what a 0 does is it doesn't contribute anything until it gets to the break frequency. Once it hits the break frequency, it goes up at 20 dB per decade. So when something contributes nothing, what is another way of saying that? 0. So this is perfectly flat here until it reaches 3 dB. So let's go ahead and let's start this here. This is 0.1, that's radians. And let's say that this is, because I got to go to 2K. Yeah, so this is 1 radian per second, 10 radians per second, 100 radians per second, 1,000 or 1K, and then that's 10K. Okay, so this is a little different. Do you notice on the x-axis, I just went linearly, right? I went 0, minus 20, minus 40, minus 60, all the way through. So I was just going a difference in 10. Over here, because it's logarithmic, I got to go 0.1, and then I have to multiply by 10. So now I get 1. Then multiply that one by 10, and I get 100. So let me get rid of the log. And on and on and on, right? Until I get to the end of the curve. Everybody understand that? Because it's very different. If you haven't done logarithmic, it can be confusing, but you have to do multiples of 10. So logarithm here is a 10 base logarithm, not a natural base logarithm. So this is 10 base. So that contributes nothing until I get to 3 dB. 3 dB is right here. That's the other thing that's a little hard about dBs, is because you can see that from 1 to 2, it's a pretty big gap. But from 2 to 3, it's a small gap. And look at between 9 and 10, it's almost illegible. So I'm going to zoom in a little bit so I can make this easier to see. And this is going to go all the way up. So let me make it less messy here. So this is flat all the way. So that's 0.1. This is 1, 2, 3. And now it's going to go up 20 dB per decade. This is the key thing about drawing these. This is 0 dB right here. This is 20 dB. So to go up 20 dB per decade, I have to stop when I'm at 30 dB, right? I go up 20, not stop, but I continue. So I want to draw a line as straight as possible from here to here, and that is 20 dB per decade. Everybody see how I drew that? So I went up 1 decade, which from 3 means I got to go to 30. And then I plotted 1 decade or 120 dB above. That's how I got that number, or that plot style. Any further discussion required on that, or does that make sense? Let's do another one, and then let's see. So let's do S divided by 50. What color would you like? Yellow, orange, light blue? Light blue? All right. So this one is going to be the dB for S over 50 plus 1. So help me out. Come on, move over here. I don't know why it doesn't want to move. Go. And I will not zoom in so much so I can't see things. So now I'm blue. This is a pole, right? This is the denominator. So we know it's going to take away 20 dB per decade until it gets to the break frequency, and then it goes down at 20 dB per decade. I'm not contributing anything until I get to 50. 50, right? 10, 20, 30, 40. Oops, I did this incorrectly. That's 3. I did this, sorry, I did the green one wrong. Let me go back and do the green one. This is not 30. This is not 30. 30 you can see is over here because I did double. So now that's 30. Sorry about that. This is 20 dB per decade. So for my blue one, I'm going to start at 50, which is, what are you doing? Stop that. Which is 40, 50. This is 50 here. So this contributes nothing until I get to 50. And then it goes up, or sorry, it goes down at 20 dB per decade. So let's move this out of the way. I guess we have to move it up just a little bit because I can't make up to 50. Nope. All right. So now I'm going to go up or down 20 dB per decade when I get to 500. Why won't this go away? Darn it. I wish I could move this out of the way. I'm going to have to zoom out a little bit because I can't see my frequencies. So I'm going to go down at 20 dB per decade until I get to 500. 500 is 200, 300, 400, 500. This is 500. So I'm going to go down 20 dB per decade when I get to, oop, that's pretty ugly. Let's try that again. See if I can do it this way a little bit easier. Actually, there's let me see if I can do the, I guess I thought there was a ruler feature in here, but that doesn't seem to be. So let's try it again this way. So that's going down at 20 dB per decade. Okay, I've got one more. So the last one I need to do is the 200. So which color do you all want for the 200? Glitter? Is there a glitter here? I can't see. This is glitter? All right, we'll try it. Blame Mason if you can't see it. How's that? Kind of purpley. All right, we'll call it Mason. Mason F. Okay. Same deal. Contributes nothing until it gets to the break frequency, which is 200, which is up right here. Then it goes down at 20 dB per decade. So it's flat until I get to 200. And then I'm going to go down at 20 dB per decade until I get to 2K. So here's that value. Hopefully that's legible. And this again is 20 dB per decade. Now I have everything I need to draw the final image. So let's pick a really bold color and a thick pen. What do you want? Can't do purple or green or blue. We can do yellow or orange or black. All right, let's make it pretty thick. So now it's just adding them up. When I start at 0 or 0.1 radians per second, I'm right here. Nothing doing. Nothing doing until I get to 3 radians per second. Now I start going up at 20 dB per decade. So I'm going to go up to 30. And I'm going to continue going up until I get to 50. What happens at 50? I've got one going up at 20 and one going down at 20. So what happens? Straight line until I get to 200. What happens at 200? I start going back down because now I have another 20 dB per decade going down. So my plot is this. And it continues going down for essentially for a long, long time. All right. Now, if you want to get really refined, you can get a little fancy by doing that 20 dB per decade or 6 dB per octave calculation. Like we know over here, we went up to 30. So at this point, we're someplace like right here should be minus 50. And then 30 to 50 is almost a doubling in frequency, right? 30 to 60. So this is around 45. So this is minus 45 when it settles out, and then it just drops forever and ever and ever. Okay? That is my gain plot for this system. I still have to do phase. So I'm going to plop that in over here. And it's the same concept. So let me go ahead and write the original transfer function kind of converted. All right, so scale factor, I don't even have to include when I do my phase plot because it doesn't contribute anything, right? It's a real number, so there is no phase shift associated with it. So the color scheme we had baby blue, I think was our first one. And let's make that down to 1. So I want the angle or phase associated with S/3 plus 1. So scale factor does nothing. So let's do this. We can start that at 0. No, we will start at 0. We'll start this at 0. This is 45, minus 45, minus 90, minus 135, and minus 180. Why don't I have to go any more than minus 180?
It's only going to be 20. Can only do.
Well, that would technically be 360, right? But the concept of it is if I have 2 poles, I have a possibility of actually going to minus 180. But because I have 2 poles and 1 0, I technically only go to minus 90. But we'll just put that, we'll start out with there, and then we'll see how cluttery it gets. So remember, this starts at 0.3 and ends at 30. And it's positive 45 degrees per decade. So this is going to be 0.1, 10, 100, 1,000, Am I off by one? Whoops, hold on. Oh, yeah, no, it's good. Wait a minute, 0.1. Yeah, I skipped 10. There we go. Or 1. It's 0.1. 10 as after 1. 100, 1,000, and 10,000. So because we want to calculate approximately where, we want to be able to compare the two, we usually want to have the same frequencies. So I'm going to start at 0.3. And at 0.3, nothing's happening before 0.3. Oh, wait a minute. I really need to make this go up one more. 90, 45, 0, minus 45, minus 90, minus 135, minus 180. Because I want to show all the plots. So it starts off at 0 until I get to 0.3. Then I'm going to go to 45 degrees at 3. And at 30, I'm at 90 degrees. This is 45 degrees per decade. And then it flattens out. This does not continue to increase, it flattens out. Now the next one was green, I believe. I think it was that color green. So this is the angle for S over 50 plus 1. Same deal. It starts out at 0. And it goes and stays at 0 until it hits 5. 2, 3, 4, 5. Then it goes down at 45 degrees per decade. So at 50, 2, 3, 4, 5, I'm here. And then it stops at 500, 200, 300, 400, 500 is here. And then it flattens out. And again, that's 45 degrees per decade. The last one I did was, you call it sparkly. So this one here is S over 200 plus 1. Same deal, doesn't do anything until it hits 1 decade above. So 1 decade above 200 is 20. So that's flat until it gets to that point. Then it goes down and hits negative 45 at 200, which is the break frequency. And then it stops at, whoops, 200 is further along. Sorry about that. $200 is here. And then it stops at 2000, which is here. And then it goes on along. I don't know why I can't draw things very straight, but each of these are 45 degrees per decade. Now we're going to go ahead and use, what was the overall one? Color, orange. And we made it a 4-point line. Orange at 4 points. All right, so now we're flat. Then we start going up at 45 degrees per decade. And at this point, we have one that goes down, right? So that flattens out until we get to 200, which is, 20, which is here. I had this stopping. Let me fix this because I had this stopping to, I had this starting too early. This goes here to here. Now I've got one going down, but it only goes down for a scotch, right? Because this it only goes down at 45 degrees for a scotch, because this one now is no longer contributing. Now I've got two going down. So it gets really, really steep until I hit here. And then it gets less steep until I hit that 2K. And then it flattens out. So this is 45 degrees. This is minus 90 and minus 45. So doing Bode plots when you are looking at phase plots are more complicated because you have to start and stop them. So like when we did magnitude plots, it was pretty easy, right? We just went up and we just kept going and going and going, or we went down, we kept going and going and going. Over here, you have to look at the starting and end points. That's why I find it really helpful to draw all the different diagrams until you get really good at it. And then you can just break it down into a table and make it hopefully a little bit easier for you all to represent those. Last thing we'll talk about for control systems. Why won't you move? Yeah. So if you remember, this is a summing junction. This is plus to minus. And we call that negative feedback, right? We know that this was the error signal, which was equal to my set point minus my feedback value. And we always wanted it to be minus because if it was a stable system, it works to minimize that error. What happened if this transitions to a positive number? You have a set point that you want, and what's coming back gets added to your set point. Does that seem like it's ever going to become a zero error? If you add 3 to 5, then it becomes 8, and then it comes back and now it's 4, becomes 9, it just gets bigger and bigger and bigger. So positive feedback is usually the way to get unstable systems. So you never want this negative here inside the circle to be a positive, because now you are actually adding your output to your set point and you get problems. How can you make a negative become a positive? Multiply by -1, right? What's another way? A plus B is this, right? What about A minus B? Sorry. I only have to carry my phone around because of this new Duo stuff. Because if you don't log in to Main Street, you can't log in. So I have to bring my cell phone around to be able to do two-form factor authentication. So that's the only reason why I started bringing it around with me this semester. Otherwise, I just leave it in my office. You do have two-form factor because you can't log into Main Street. You can?
Yeah.
Well, Noah maybe told us a fib then, because he said they hadn't enforced it, but they were going to start enforcing it like last week or the week before. So what's that?
I think it was only faculty.
Oh, I thought students had to do it as well. What was going on with that? I love cell phones, so smart. So that's A plus B, right? What if I want A minus B? How do you solve for A minus B? This is A. Is it minus B like this? You phase shifted 180 degrees, right? Isn't that taking the negative of a complex number? Oh, somebody have some feedback? Oh, only required for students with a mobile main card. Thank you, Noah. Sorry, I was going to give Noah a hard time because he told me last April. He said April. Yeah, it was 2 weeks ago. So students, you get priority service, right? You don't actually have to. He said it's only required if you have a mobile main card. You have an old school one, so. Yeah, they got rid of making main cards. Everything now is mobile. Well, so the way that you add negative vectors is you phase shift by 180 degrees. So this becomes a negative number by phase shifting it by 180 degrees. So that brings up a concept. If, right, your gain of your system is greater than 1, and your negative feedback becomes positive, I mean, your negative feedback becomes positive, then you have an unstable system. If the gain is less than 1, it gets smaller and smaller and smaller, right? So 20 log 10 of 1 equals 0. So if I have a plot that does this, and let's say this is, I don't know, let's say it's 60 dB. That's my magnitude, right? This is in dB. And I have an angle plot. And let's say that it's going down, 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 then really steep, then settles out, and then maybe does one of these and settles out. Now, my concern is, when do I hit minus 180? Because anything down over here means you can have negative feedback. That's okay as long as I am on this side, if I'm 0 dB. So you can see at 180 degrees, let's say that's over here, or minus 180 degrees, my dB is above 0. This is an unstable system or potentially unstable system. So this system wouldn't fly. If, however, I went with something like this, and I had this over here, and this is, let's see. Let me make that a little easier to see. You can't see it from here. Whoops. My erase button doesn't seem to be working all that well. And let's say it reaches 180 someplace over here. If I look at my 180 point, I'm below 0 dB. So this point from here to here, between 0 dB and this point, that is called my gain margin. What my gain margin is how much I can multiply that by, how many dB can I add to it, or how much can I multiply it before this moves up, when that point moves up to 0 dB. That's gain margin. Okay? Phase margin is when I'm at my 0 dB, let's say I'm at minus 135 degrees. The phase margin is what the difference between minus 180 and here is. So I can actually introduce some phase shift in the system before I have to worry about being an unstable system. Okay? So to determine phase margin, it's where it crosses 0 dB. That's when you determine phase margin. So when you're at 0, and this is only for stable systems, you're at 0 dB, and what your actual, your minus 180 point is. And then gain margin is when I'm at minus 180, what's the actual gain of the system? Okay, those are two control terms that you would use because you would add some feedback to the system. Okay. Any questions on that? Because that was kind of the last thing I wanted to get for doing Bodie plots. Because you might be saying, why are we doing Bodie plots in a controls course? Right? Because it's more of a filtering type thing. But you actually have some systems that are AC. Like a perfect example is when I worked on nuclear power plants all the time, they had this little sensor. And when there was a crank that was spinning on the shaft of the generator set, it would have a little magnetic pulse. And that was a frequency, and it would tell you the speed of operation. And so the input was, I wanted a set point speed of, let's say it's 260 hertz of pulses. What was coming back might have been 255. So it would say, hey, we need to add more fuel because what's coming back is less than 260 hertz. But if going through the system and it was coming back and it was actually positive feedback, now it's actually going to increase until the system becomes unstable. Okay, so that's why we cover Bodie plots in control systems. And actually doing Bodie plots, and I know you might say, wow, that's a lot. But if you remember when John covered, I think in 342, Bodie plots are really, really easy when you do the asymptotic approach using the Laplace domain and just substituting in JWave. All right, any questions? We only had 2 classes on Bodie plots, but again, you might see it on the FE. You might see it, especially in power systems, because we're starting to look more and more at transients, switching transients. Anybody pay attention to what's going on in Spain and Portugal right now? People watch the news? Or
The cascading blackouts.
yeah, they've had power losses for days. And you know what they said was a problem? Oscillations in the power system. That's frequency oscillations. And those systems weren't able to stay online. And, you know, we think, oh, losing our power at a house because of a bad storm for a few hours is bad. When the whole country is without power, that's a major, major, major problem. They were talking about like at traffic lights or street corners, how they would have civilians actually directing traffic, because can you imagine if we were getting off, trying to think of a good application in Maine, or in, I should say in Bangor, that you all are familiar with, that gets really totally traffically. How about Broadway? Anybody know Broadway in Bangor? Right where the 295 or the interstate, the 95 drops you off and you got to jump on Broadway, and you got cars going in both directions, and some cars trying to turn left, some cars trying to turn right. Can you imagine if people were trying to direct traffic without the stoplights? How many accidents and how bad traffic would be? And that's just small part of it. They have electric trains there for their subway systems. And so literally they said people were exiting the subway systems in the tunnels and then walking out. I don't know how far, how long, but that's how they were getting back and forth. And last month we saw Heathrow in London had a power outage because of a fire, and it affected air traffic all over the world. And so we're starting, hopefully, should have realized this a long time ago, but we're starting to realize, wow, electricity is really important to make our lives function effectively. And it's partly because we've become so dependent on it. I was reading an article today about somebody who was doing an off-grid home, which is perfectly fine. You can do that, but what if your off-grid system fails? If you become dependent on it, you might have some serious problems there. So it's just a different perspective about things. So as our grid becomes more and more renewable, and you can say with the current administration that may or may not happen, but things change a lot in 4 years. At some point, we will run out of fossil fuels. I'm sure of that. I don't know if it's going to be tomorrow, but at some point we will. Especially when I see somebody, like I saw somebody the other day driving around in a 6.2 liter. It was a Dodge Hemi. And then I looked it up and it gets 12 miles per gallon. And this is a, what's that?
That's what I get.
That's what you got?
Yeah.
But if you know, that's maybe 10 people, right? Because those are very expensive vehicles, I think. Can you imagine if everybody in the United States had a vehicle like that, how much more expensive gas would be? I'm part of the solution. My Prius right now, I've got 430 miles on a tank of gas, and I've gone 63 miles per gallon. It is ugly, but when I wave at the gas pump, or when I fill up my gas, it takes usually no more than 8 gallons to fill it up.
25, that's for me to fill it up, but I had mine at like 25 max.
Yeah,
It never all.
but we're part of that. But and again, Mason and I, we're part of the solution. Not anymore. But the idea is, and again, it's not it's being a little bit flip, right? I'm not saying I'm not all that good, but the idea is you actually are saving costs to other people. That's why one of the things I don't get, this is a political thing, which is why are you upset that I'm driving a Prius? It actually, if you're driving a 3/4 ton dually, whatever, why do you care that I'm using less gas? It makes the gas cheaper for you. Hey, you want me to use more gas, and it makes gas more expensive. So people flip you off and do all this stuff when you're driving a Prius, but it's like, why? I'm going the speed limit like everybody else. I'm not in your way. Why does it make you mad that I'm using less gas? I don't understand. No, I'm going the speed of traffic, right? So if you're in town or on the highway, you're in the right-hand lane and you're doing, I don't know, 75, whatever, and most cars are doing 75, and somebody buzzes by you and honks their horn and flips you off. It's like, or the same thing if I'm riding a bicycle going through town, I'm riding a bike and I'm not blocking the lanes. I'm just on the side and people will honk their horns and flip you off. I'm like, why do you care? I'm not in your way. I'm actually taking less traffic if I'm commuting, less cars. So again, it's not a judgment thing. I just don't understand it. So maybe somebody can explain it to me. He drives a gas guzzler and doesn't like to see bicyclists or Prius on the road. I don't get it.
I think there's sort of the amounts of less ugly cars that, like, if they make the Prius look
Not
nice.
like, yeah.
The new one looks pretty good, they say.
The ones like, if they need a big streets, I'd buy that. The new ones are bad.
Because they're heavy.
Yeah.
I like mine, like,
Yeah, mine's like generation 3, so mine is the ugly version of the Prius, but again, you don't have to, you're not riding around in it, so.
Presented in a Hellcat, I'll take that.
In a Hellcat? I think I think that defeats the purpose of the Hellcat, because yeah, one of my son's soccer buddies, his dad has a what's the pickup truck version of it? I don't know what it's called. He's the one with the TRX. He's the one with the 6.2, and he had to drive to Pennsylvania pulling a thing, and he was like happy that he got 10 miles to the gallon. I'm like, wouldn't you have more fuel efficient vehicles? Oh no, that engine revs. You can tow the Prius?
Yeah, he welded on it. He said he got like 20 some odd miles per gallon, but it was industrial oven.
Oh, I don't plan on doing that. So anyway, I've been yapping long enough. Any questions? This is our last class, because on Thursday we'll do an exam review. Everybody know when the final exam is? I don't have to post this, right? Because everybody knows that the University of Maine, I think we've talked about this in the past. It's all determined by student records. We have nothing to do with it other than we tell them we would like a final or not. And all the scheduling is done by student records. So if you are unhappy with when our final is in this class, I had nothing to do with it. So don't complain to me. You can go to student records and complain to them. But EET 325 is right here. So it's in this room, 10:30 to 12:30 on the 6th of May. The 6th of May is week from today. So in 1 week, you'll have your final exam. I just have to figure out, should I put Bodie plots on it or not? What do you think?
Are you gonna take off something else that's harder?
I don't know. I gotta figure it out. But I'll put together the final exam stuff, and I guess I'll think about it, because you haven't had homework on it. That's the only reason why I'm not really keen to do Bodie plots. If you haven't had homework on it, it doesn't really sink in. So.
I'll go print off that contract right now. Can you sign it?
Yes. Am I not sharing my screen anymore? I should share. Oh, no, I am sharing my screen. Okay. All right, so you know the final exam? You get a full 8.5 by 11 sheet of paper, double sided. Or just single sided if you feel.
Oh, thanks.
All right, y'all. Have a wonderful day. It's supposed to be beautiful weather today. I'll see you on Thursday. Take care, everyone.